Okay, welcome to part 2 of Newton's method. In this segment, what we're going to do is we're going to take this sort of simple program and we're going to functionalize it or put it in a script and then allow you to input parameters to kind of easily use this functionality. So let's just kind of recall what we did here with Newton's method. So we have x squared minus 2 as our function, and the two solutions to this, or the two roots of this, are 1.414 dot 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 and the negative of that. And so these are plus and minus square root of 2. So square root of 2 is an irrational number, but we can numerically approximate it using Newton's method. And so what we did was we showed, oh, okay, well, if we have a bunch of tangent lines, successive tangent lines, then we can get closer and closer and closer, and that's exactly what we have here. And so we've got a 2, 1.75, etc. So I changed this to a 3. So here this is converging towards the square root of 3, and indeed it does. And so if we look at just the last entry, they match. So, okay, so we'd like to create a function now that would use Newton's method to find the square root of any number. So there's nothing special about 2 or 3. We could do square root of 15 if we really wanted to, and etc. So let's create a script. So you can create a script in a number of different ways. My preferred way is to right-click on the cell number on the left. So if you right-click again, it goes back to a normal cell. The other method which you have to do on the iPad is to click on entry and then do script, and it's the same thing, it shows up. So now that we have our script, let's call this one square root, and we're going to take a square root of a number a. Let's call it a, and then because we're talking about Newton's method, this 10 here plays the role of the iterations, and so that's either denoted by, usually it's iters or n. I like to stick with just n, and we have the beginnings of a function, so we do a shift enter a bunch of times, and we've got some lines to work with. So the first thing I want to do is I want to set the function properly. So I want to have f of x be x squared minus a. And again, the reason we do this is because when x squared minus a is equal to 0, mathematically that gives you the solutions plus or minus square root of a. So what we want is to use Newton's method, which then converges to those roots. And so if we're going to do that, we need an initial condition, x naught. And there's different schools of thought on this, but the predominant one seems to be, for the square root function, use an initial condition of a, which seems reasonable because a could then be some very large number and you're in the right ballpark for converging towards it. If you have no a priori reasoning what the initial condition should be, typically you use a 1. Or if it's a multi-dimensional thing, you use a vector of 1s. I've seen that common. We're just going to use an a for now. And so then what I'm going to do is this loop up here uses the lists and keeps an eye on each entry. And I'm not going to bother keeping tabs on that. I'm just going to loop through this n times, and I'm going to replace the current value of x naught with x naught minus f of x naught divided by f prime of x naught. And again, all I'm doing is this formula comes from this up here, and just replace your sort of list notation with just, okay, well, we're going to overwrite the value at each step. So you've got this, and then the last line should be the value you want to return, and that's going to be x naught. So we can't just push the arrow key down. It's not going to work. We have to go is into the script itself and hit enter. Now that we've hit enter, we've essentially compiled this function. we've basically told SpaceTime, okay, that's the name of the function, this is what we want it to do. And now we can try it out. Square root of, let's do 5, and let's do 10 iterations. Okay, it gives us an answer. Let's compare that with square root of 5. Oh, and there we go. Okay, so they match, which is good news. So one slight variation of this that I want to introduce, which can be really nice, is, okay, well, how many n is enough? Maybe we don't want to specify the number of iterations each time we use this function. So maybe we say, in general, 10 iterations is, more than enough to converge to an accurate enough solution. So we do a n equals 10 up there in the parameter. And this tells us that, so we have to hit enter first to get it to compile. This tells us that if there is no second argument, just put in a 10. But if there is a second argument, say only 3 iterations, we'll use that for n. So it can be nice if you want to suppress some detail, but then still want to include it for more advanced functionality. So let's go back to 5, and we get our nice accurate answer. So the other thing I want to point out too is the reason I looped I from 1 to n was because previously up here we needed it to index the element in the list. When we're just overwriting the values, there's really nothing here that depends on I. And so what we can do is we can replace this with just a loop of n. And what it does is for n, a numerical value, it just runs through this code n times. So let's give that a try. So, okay, nothing very exciting, nothing's changing. But again, we go back and we plug in the 3 that we did before, and it does exactly the same thing, which is what it should do. We do that, and we get numerical answer. Okay, so again, if let's say I wanted to change this to cubed root, I could do x cubed here, and I could write another function for that. Or what if I wanted to do whatever function? So the point is that, okay, well, if I have a specific function in mind with a single parameter, this could work quite well. Or another thing I'd like to be able to do is input a function itself. And so that's pretty easy to do. There's only one thing you got to be pretty careful of, and that is getting your variables right. And so let's call this function Newton root. This is going to be my Newton's method to converge to a root. So what we're going to want to do is input a function, f, and then we're going to want to input the name of the variable, x. And I'll show you why after we go through this example, but let's just start out in good practice. So we're going to have a function that's going to be defined in terms of a variable, and then we need an initial condition, let's call it a, and then number of iterations n, and let's force n to be 10 if we don't want to think about it. So let's get some lines. So first, what I want to be very careful about is I want to be able to input a function and specify whatever variable I want to call it. So let's say I want to compute the root of sine of x. Okay? If I want to compute the root of sine of y, well, I want it to return the same thing. And so what I don't want is I don't want x to be a special character. I want to be able to define a function in terms of any variable, whichever name I give it, as long as I just specify what the variable is going to be called. And so the way we get away with this is we do, let's define g of x, a new function, to be the evaluation of f at the variable x. So what this is going to do is you're going to input an expression for f in terms of some variable. You're going to input the variable as a second component, and then everything is going to work internally, so you don't have to think too much about it. So let's let our initial condition be given by a, and then we'll loop through this n times, and we're going to have x naught is equal to x naught minus g of x naught divided by g prime of x naught. And we have end, return x naught, and then make sure we hit enter. So let's test drive this function. So Newton root of, so let's do x squared minus 2. Our variable is x. Our initial condition, let's say, is 2. And we'll leave iterations blank. So it'll be by default 10. Oh, and there we go. And again, a quick check. We get the same answer. So now let's be a little more adventurous and just say, okay, well, let's look at the cubed root of 2. And we get that. And then, let's see, I forget, I think our square root function, okay, it only takes one argument. Root, n root is a function. This is a good opportunity to bring up the function n root. Let's see, so we give a number, say we're doing 2, and we're doing the third root. And so what it's going to do is it's going to give us all of the roots, not just the real valued one here. So Newton's method will only return one root. And if you start it with the real initial condition, it'll return a real valued root. But also what's kind of nice is, the question you might ask is, well, what if I gave it a complex initial condition? Would it converge to a complex root? So let's give that a shot. So the beauty of SpaceTime, I mean, I really like to use it because of these really niceties. I don't really have to do that much to go between complex numbers, real numbers, etc. So let's start at, let's say 2 plus I, and see if this works. So let's go back to, okay, let's keep this example and do, okay, so we converge to the real root again. Let's see, let's try doing negative and see what ends up. Yeah, there we go. So Newton's method can be very sensitive to initial conditions. And so here, when I've started in the right place, I've converged to, that's a plus. So this guy here, this middle guy, converged to one of the other roots. So this n root function is great for, the n root function is sort of answers the question of, well, wait a minute, the cubed root, or let's do the square root of 2. Well, let's do 9. Okay, square root of 9 is 3, and you might say, what about plus or minus 3? I want to return all possible sort of. You got to be careful with inverse with square root, but I want to return all possible square roots of the function, x squared minus 9. Okay, so the solution to that is to do n root. We have the z would be a 9, and we have a 2, and we get our two solutions minus 3, comma 3. There's a reason why we always return the positive square root for a number like 9. I won't get into that here, but there is a very good reason why square root of 9 should not return this minus 3 or plus 3. It'll always return the positive solution. Okay, so that is sort of a way to generalize it. So let's test it on something other than a polynomial. Newton root of maybe sine of x minus x variable. Let's call it something other than x. Sine of y minus y. Variable is going to be y, and we're going to start at, say, 1. Okay, and there we go. We get a root. We can change this to a plus y. And, of course, y equals 0 will give us 0. So y is let's try minus cosine of y. And there it is again. So this actually is a very interesting point, because this is the point where sine and cosine meet. So this is a point that you may have seen before or may come up at some point. So that's the gist of it. Again, if you're sure that you're always going to be inputting a function in terms of x, then you can tailor fit your code to that. If you want to give the user the freedom to input whatever variable or name it, I use this example a lot when I teach, is I can call my dummy variable Frank, and everything stays the same. Everything stays the same. Okay, so you've got that, and okay, that's all for now. But Newton's method is really rich in applications. So I'm sure we'll come back to it.